guys, and welcome back to the channel. In this video, I thought I would try something different, and we're going to be building a simple but functional operating system from scratch. We'll talk about what is an operating system and why we need one in the first place. Then, we'll strip bare our computer of all software, and we'll look at how the processor works, how the computer boots, how to write low-level programs where no operating system exists yet. We'll also look at how to bootstrap code written in a higher level language like C. And yes, C is a high-level language, at least compared to what we'll be working with. And we'll also look at how to write some basic device drivers. So that's a lot of ground to cover, and I imagine this is going to be a multiple-part series. So without wasting any more time, let's get started.
Alright, so let's talk about what is an operating system, and why do we need one? Back in the old days, and I'm talking about 1950s and earlier, we had these huge machines. And by huge, I mean they could take up a whole room. People used to refer to these as the brain. And if you wanted to write your program on one of those, you had to write all of the code for interacting with the hardware yourself. That means you had to tell the disk drive when to start a spin and read data from specific sectors and cylinders, and you had to turn off the motor yourself when you were finished doing your I/O operations by writing to a specific register in the processor. That may not sound too bad because you could write a routine to reuse your code and write abstractions for these low-level interactions, but there are a few drawbacks. For one, you would need to bundle these low-level libraries or drivers for every program that you wanted to write, making your program unnecessarily large. Also, every single person who wanted to write a program had to basically create their own little operating system first, unless you could borrow one from your friend. So soon people started to realize that we need some kind of a common system, a system program, if you will, that would provide us with a nice basic API interface where we wouldn't have to re-implement it every time we wanted to create a program. Wouldn't it be nice if we could just call a write function from somewhere in the system program and it would write to the screen and even scroll the screen, all behind the scenes? How much more productive we could be. And that's exactly what people did. An operating system is simply a program, like any other program on your computer. There are generally 5 types of programs running on your computer right now. There is the firmware program, like the BIOS, whose job is to load the bootstrap program. And if you want to learn more about how a computer boots, check out my other video. The link will be in the description. The bootstrap program is very small, and its job is to load the bootloader program, which provides a user with a choice of which system program they want to start. All the other programs running on your computer, which use the APIs provided by the system program, are called user programs. On modern operating systems and processors, the user programs are set up in such a way that they cannot directly interact with the hardware without entering a higher privilege level and calling one of the APIs provided by the system program. At its most basic level, a computer program is nothing more than a sequence of instructions for the processor. At the hardware level in your computer's memory, these instructions are represented as charges that go through a pre-wired logic gates to alter other memory cells. If you want to learn more about how a computer works at this level, I highly suggest the video series by Ben Eater where he built an 8-bit computer using nothing more than breadboards and logic gates. The link again will be in the description if you want to check it out. So we start our journey when we reboot our computer. It must start up again, without any notion of an operating system. The first thing that will get loaded into memory will be our BIOS program. BIOS will complete some low-level tests of our hardware and load the first sector, or the first 512 bytes, at cylinder 0, head 0, and sector 0 from the first bootable disk. BIOS recognizes that a disk is bootable if the first sectors end with 2 bytes of alternating ones and zeros, or 55AA in hexadecimal. The 55 in binary is actually 01010101, and the AA is the opposite, 10101010. That way there is little chance that the first sector would end up being anything other than the bootstrap code of a system program. And this is where we take over the control of the computer. By writing our program to the first sector of our hard drive, it is now our program that is running on the computer. The most basic operating system that we could write, and the start of any operating system, is to make it bootable. We already know that our program needs to be exactly 512 bytes long, and the last 2 bytes needs to be the alternating ones and zeros. So let's go ahead and open up a text editor and we'll begin writing our operating system. But there is one problem. A regular text editor usually cannot write raw bytes to a file. It uses an encoding to translate your text to binary. However, the encoding doesn't map to the same binary output as we might expect. You might think that writing 1 will also produce 1 in binary, but actually it will be saved as 00110001, and 0 would get saved as 00110000. So we need an editor that will allow us to write actual binary to disk. I'm going to be using the Bless Hex editor, which does require us to write in hexadecimal, but we are going to be able to see the actual binary data once we save it to disk. So at this point, it really doesn't matter what comes before the 510th byte, as long as the last 2 bytes are our magic boot number. So we can simply fill the rest of the sector with zeros. 1 byte is actually 8 bits, so we're going to need 4040 bits of zeros before you get to the 511th byte. And finally, we put our magic number 55AA, which in binary is going to be 01010110101010. The BIOS program will look at these 2 bytes to determine if it is a valid boot sector. Let's go ahead and save our boot sector to a file, and we're going to open it with a binary editor to see the raw binary output. As you can see, the first 510 bytes are all zeros, followed by our magic number of 01011010 and 10101010. Congratulations, we have just created a valid boot sector. Well, that's a bit of a lie because our program is not actually a valid program because we haven't given any meaningful instructions for the CPU to execute. Let's do that right now and create an infinite loop that will permanently hang our program. Now, I'm using the x86 CPU architecture, so I'm going to look up what the instruction, also called the opcode, is for the jump instruction. I want it to jump to itself, so I'm going to look for the relative jump instruction, which for my architecture turns out to be E9 in hex, or 11101001 in binary. And it takes the next 2 bytes as an offset. That means we'll need to jump 3 bytes back to the jump instruction. Great, so now we have a valid boot sector that doesn't do much, but every operating system started out this way. We're going to build on top of this in the next videos, but it's time now to burn this on some kind of storage device and tell BIOS to boot our just created program. You can also use a CPU emulator like QEMU or Box. I'm going to be using Box, so I first need to create a configuration file and specify the program that I want it to run. Now, all I have to do is open up the terminal and run Box. And just like that, our very first operating system is now running on our machine. We can even see the instruction that it's currently executing, which is our infinite loop jump instruction. In the next videos, we are going to be building on this foundation to create a more functional system program. Don't forget to subscribe if you like this video, and I will see you guys in the next video.